потянутся. Today we continue our studies of stochastic derivative and extended or Skorokhod stochastic integral in a special case when we consider not abstract Hilbert space and Gaussian white noise in it. Namely, today we discuss the functional from the standard Wiener process. And let me recall you that in this case we have the following picture. So we have Wiener process. For simplicity, I consider one-dimensional case. We obtained the following representation for any random variable alpha, which is square integrate and measure with respect to Wiener process. The alpha can be uniquely represented as a series of the form here we use the following notation. Where these integrals, of course, are not Wiener integrals because here we have the intervals 0, 1 for any parameter t1, tn, but it was defined like follows. There is n factorial and then integral theta n, an t1 tn, dw t1 dwtn. Here is simplex delta n, where the variables t1, tn are ordered in increasing order from 0 to 1. And we suppose that kernels an are symmetric and square integrate. This form of the representation of alpha is useful because in such a form we have the following good relation for the second moment of alpha, namely expectation of alpha square now is equal to the sum from n equals 0 to infinity, n factorial multiply the two norm of the corresponding kernel 0, 1 and an t1 tn square dt1 dtn. So we have the following representation, which often called Wiener representation. And in terms of this representation, we began to discuss stochastic derivative of the different functionals from the initial Wiener process. Initially, stochastic derivative was defined as a random function of the following kind. d alpha, this is a function, so its dependence g, is equal to the sum from n equals 0 to infinity, and here is n minus 1 integral from the kernel Pn, where the first coordinate inside of the kernel is the same t as here, and t1, tn minus 1, then dw1, dw minus 1. This is definition which we get from the general picture when we have a Gaussian white noise in the separate Hilbert space. But since we have a representation of integrals, then it looks like we will have special properties, special representation of such stochastic derivative for special given integrals. It is true, and last time we discussed representation of stochastic derivative for the maxima of the linear process of the interval. And today we will continue, namely we will study stochastic derivative for solution to stochastic differential equation. So we will begin with the stochastic derivative of Ito integral. Namely, I will consider a following case. I will suppose that our random variable alpha is integral from 0 to 1. Here is xt dwt, where now xt will be a random adapted square integrate function. X is a random square integrate adapted to the floor ft generated by the path to the inner process. T is belong to 0, 1. And our aim will be to discuss stochastic derivative of this random variable. Of course, we have to start from some simple case. And from the beginning of our studies at the university, the simplest case of the integral construction is the integral from the step function. So now let me consider the example of such stochastic integral, and we will discuss its stochastic derivative, if it exists, of course. So let us consider the example. When xt is equal simply a sum of k equals 0 to n minus 1 alpha k, maybe alpha is not a good letter, beta k, multiplied on the indicator k over n, k plus 1 over n. So this is a step function with the steps related to the uniform partition of the interval 0, 1, and beta k are the random variables. Only we have to check some conditions. Only we have to check some conditions of non-beta in order that x will be adapted square integrate random function. Square integrability will hold if we require that beta k belongs to A2 for k equals 0 to n minus 1, and when x be adapted, of course, it will happen when beta k is measured with respect to k over n. So when we discuss the graph of our random function, it looks like a usual step function graph. Then this is, for example, k over n, k plus 1 over n. This attitude, beta k, must be dependent only from the past of the linear process. So we have such two conditions of the beta k, and under this condition, xe is exactly such function as we discussed, and the sum from k equals 0 to n minus 1, beta k w k plus 1 over n minus w k over n is exactly the integral from 0 to 1 xt dwt. And when discussing stochastic derivative of such kind of integrals, we have to look at the sum. And here it is very natural. It is not only one possible way, but it is very natural to look at just one summand here and ask when this summand can have stochastic derivative. And it seems that the simplest condition, sufficient condition, is the following. Suppose that beta k has stochastic derivative. That beta k has stochastic derivative, and then use the property of stochastic derivative to satisfy chain rule. So if we have product of two random variables, then the stochastic derivative of the product looks like the usual derivative of the product from the analysis. So let me check. Let me check what will happen here. I suppose now that alpha k belongs to W1. Let me recall you that by the such symbol we denoted the set of all stochastically differentiable variables. And then I am claiming that there exists a product, a stochastic derivative of the product alpha k. Here is w k over k plus 1 over n minus w k over n, and it is from d, and it is equal to d alpha k from t multiply on the w k plus 1 over n minus w k over n, and plus alpha k, excuse me, sorry, we have to put n in beta k. Please correct this. Because initially we had notation alpha for our integral. So beta plus beta k multiply with the indicator, the interval k over n, k plus 1 over n from b. So what we have to check here? What we have to check here? Only the square integrability of the obtained result in the right hand side. Why? Because you remember that stochastic derivative, closed operator. So if we have here a square integrate result, then of course I can use here some bounded random variables, bounded stochastic derivatives, and then do some approximation. Yes. So it is enough to check that the obtained result is square integrate random function. And I claim that it is true. Why? It is evident that we have to discuss only this summand, and let us consider it more precisely. So what we have? We have such a product d beta k d, and multiply on the w k plus 1 or n minus w k over n. Now let me recall you that we have additional condition on the variables k. Namely, they are not only square integrate, but they are adapted to the flow of the process. In our case, this means that beta k is measured with respect to the sigma field f k over. So it means that if we consider Italian expansion of the variable beta k, then it can be written as follows: the sum from in n, maybe not n, but m equals 0 to t, and here is now keep integral from 0 m, but not to 1, but only up to t, up to k over n. This is main new feature of the e-to-winner expansion of the random variable beta k, because it is measured with respect to the past of the winner process. So we have such kind of representation: b m t1 t m dw t1 dw t. So we have such representation, or if it is not canonical representation, not up to 0, up to 1, then one can write the integral up to 0, 1, but say that this curve bm is equal to 0 when maxima of this variable T1 Km is over the K over N. So we have such representation. From this representation, it follows that when I will consider d beta from T, let me do this just with erasing something, then I will get the following representation. And from this representation, it is evident now that d beta k as a random function is also measured with respect to the same Gaussian mapping f k over F. This is a main property which we need here. Why? Because using this property, one can now say that here we have two independent multipliers. Yeah. Then since they are independent, when I will consider expectation of the squares, and here is square, then I will get the product of the expectations. So I will get 1 over n, this is this square, and expectation of d beta k t square. Now, it follows from this relationship that obtained formula for stochastic derivative works and gives us the square integrable random function, namely the stochastic derivative of such sum from k equal 0 to n minus 1. Here is beta k multiply w k plus 1 over n minus w k over n from t is equal to sum from k equal 0 to n minus 1. Here is two summands. The first one d beta k from t w k plus 1 over n minus w k over n plus the sum from k 0 n minus 1, and here is beta k, and here is the integral indicator k plus 1 k over n k plus 1 over n. Okay, I split the expression of our stochastic derivative for two sums because we understand that now we'll do approximation of the general integrand x, and maybe we'll try to pass to the limit in this expression. So I will suppose that we have the following approximation that xn of t, which is equal to 0 to n minus 1, beta k, or indicator k plus 1 n t are such that two condition hosts the first one that expectation, the integral from 0, 1, xt minus xnt square tends to 0. This is one. The second one is the same, but about stochastic derivatives. Why we need second condition? Second condition is necessary because we remember that we discussed in general abstract setup that stochastic derivative is not a bounded operator. So we cannot say that, okay, let this function satisfy this condition, then the stochastic derivative will converge to stochastic derivative. No, it's not true at all. So we have to require this condition, and it is here, the integral from 0 to 1 dx ds minus dx and ds square dt ds also tends to 0, and tends to. Why I have here two integrals? It is clear because one is argument of the stochastic derivative, another one is the argument of the, our random function. So we have two variables, t and s. And one can ask why such a good approximation exists, but in case when x is stochastically differentiable, as I said, a good candidate, and actually this is true, for such a kind of approximation is the following: x and t is n multiplied the integral from okay, k minus 1 over n, k over n, x r dr, when t belongs to the interval k over n, k plus 1 over n. You see, I used the usual averaging construction. Only one interesting feature is here that when I'm trying to construct approximation function on this interval, I take average of the function x on the previous interval in order to keep adapting this. Yes, then please check as an exercise that this function xn satisfies this condition which we need. Okay, then having this, I can continue our consideration. And now let us write the stochastic derivative of the integral from xn. Now I will try to avoid the sum, sign of sum in the representation of the stochastic integral for xn. Namely, I will have the following. stochastic derivative of the integral 0 to 1 x n t dwt. This is our random variable, and I will put here brackets. And in order to emphasize that we apply stochastic derivative to this random variable, and we are calculating it's the point S. It's the point S is equal to let me write this first. Xn at the point S plus the integral from now let me I will put here k with star over n to 1. Here is dx n t s dws. So here I'm trying to avoid sums in the right hand side in order to get the form of the representation which will be suited for passing to the limit. And if you recall in your notes what was two summands related to stochastic derivative of this integral, then you will get exactly indicator here is beta k, indicator of the interval from the S. Yes, from the S. And it is evident that we have, and if I have k star, k star plus 1 over L, such that it contains S, then we have exactly extent of S, and we have this integral. Now it's easy to pass to the limit, and let me do it just formally. You have to check everything is okay with the convergence and square mean, and passing to the limit when n goes to the infinity, we will get the following form: the stochastic derivative of the integral of 0 to 1 xt dwt s is equal to x of s plus the integral from s to 1 d dx t s dwt. This is the final formula, and let me recall that S here is the argument of the stochastic derivative. T is the argument of our random function. So, as you remember, here, when we calculate stochastic derivative of the dxt, in any point S, we get the random variable which is adapted to the past of the Wiener process up to the moment t. We discussed this. Since then, this is a usual Ito integral. This is just the value of our random function. Of course, if it holds as inequality for random functions, square integrable random functions, so with probability 1 and almost sure with respect to the back measure. With this representation, we can continue with our consideration related to the stochastic differential. So now let's go to stochastic differential equations with the linear process. I will consider a case of good coefficients, and maybe it is reasonable now because I want to have stochastic derivative. So let me recall you that stochastic derivative is in some sense a derivative with respect to probability argument. We already discussed the shift of random variables. So it is clear that when we discuss derivatives from our object, we have to get smooth object, and in order to get smooth solution of stochastic differential equation, we have to consider smooth coefficients. So I will consider two functions. I will consider today just one-dimensional case. So these are such kind of function. They are bounded together with the two derivatives. A plus B plus A prime plus B prime plus A2 prime plus B2 prime, they are less than some constant. Yeah? And of course, this function are continuous with their derivatives. Now I'm considering stochastic differential equation. dxt is axt dt plus bxt dwt. I will start from some real number x0. So, x0, which belongs to R, let's fix it. And we know that this Cauchy problem has a unique solution which can be obtained by the iteration method because of good properties of the coefficients. Actually, this is one of the main ideas of the first year course of ordinary differential equations, that if we have Lipschitz coefficients, maybe we will have a solution with good properties. More or less the same holds for stochastic differential equation, as you know, since I can consider the solution, and since the solution can be obtained as a limit of successful iterations, one can say that solution xt now is a square integrate functional from linear process. Since this, we must have the following things. It must have linear expansion, and what is much more interesting for us now, it can have stochastic derivative. So the question is, what is stochastic derivative of this solution? By the way, the linear expansion also is very, very interesting, and we will look for this thing. But let us begin with the form of derivative. To get the stochastic derivative of the solution to this Cauchy problem, I will write it in the integral form. So x now is equal to x0 plus integral from 0 to t a x dr plus the integral from 0 to t b xr dw. Now let's try to calculate stochastic derivative, and I will do some more or less formal calculations. For example, I will say that stochastic derivative of this integral is equal to integral from stochastic derivative, put it inside, and so on. Please check that everything can be done under those conditions which I mentioned for our coefficients. So let us, for at least formally, try to get some relationship for stochastic derivative of our solution. To do this, I will take S and apply the stochastic derivative to both sides of this equation. So I will get dxt from S is equal. This will cancel because of this is just a deterministic number. The integral from 0 to t, and here I will have d a x r from S d r then plus now I'm taking the stochastic derivative at the point S. You remember how looks like stochastic derivative of the Ito integral. So it will be the b x s. Here, formally, I have to put the indicator that t is greater or equal than s, at least. Why it is so? Because you remember that if we have stochastic integral, stochastic integral, this function is adapted to the flow of the Wiener process. And if we have, for example, r, which is less than s, then xr belongs to, is measured with respect to fr, and the stochastic derivative xr, which respect at the point s, is equal to 0. Yes, you remember this form was for Ito-Wiener expansion of such random variable. We have the integral up to the moment r. Then when we substitute the s, we will get 0. Yeah? So I have here this one. Also, I can correct this 0 to the s. Now, s, and then plus the integral from s to t. D b xr from s dw, and of course now we can apply chain rule to these terms, yeah, because here we have the stochastic derivative function from the range. So finally, we will get the form. That, as we mentioned, dx ds is equal 0 when t is less than x. In opposite case, we have the following relation. dxt at the point s is equal to bxs plus integral from s to t a prime from xr multiplied by dxr at the point s dr plus the integral from s to t b prime xr dxr from s dwr. So in this place, I used the chain rule of stochastic derivative, and also let me recall, you discussed it already, that this random function, that s is fixed, is adapted to the flow of the Wiener process. So this is good integral here. The first one integral is just Lebesgue integral, and now one can recognize in this formula the linear stochastic differential equation for a known stochastic derivative. Namely, let me introduce just for a moment simplest notation. So let me denote for a moment yt with the index s, it will be stochastic derivative of xt at the point s. Then we will have the following relation. I just rewrite this formula in this notation. The dst will be equal to a prime xr, excuse me, xt, a prime xt multiplied yst plus again dt plus b prime xr ys xt yst dwt, and we have the initial condition that ys is equal bxs. So we have a good Cauchy problem for a linear stochastic differential equation. Why I'm saying that it is good? Because the coefficients which we have here, a prime, b prime, are bounded. So we can easily get the solution. And the solution is the stochastic exponent. We already discussed this, that using Ito formula, for example, one can easily check that this Cauchy problem has unique solution, and this solution can be written as follows. This solution can be written as follows: that ysd is equal to bxs multiplied with the exponent, and here we have sum of three integrals. The integral from s to t a prime xr dr plus the integral from s to t b prime xr dwr and minus 1/2 of the integral from s to t b prime xr squared dr. term and the solve. So we have the whole expression, and let me just say that this is exactly the stochastic derivative of our solution to initial problem dxt at the point S. So we get the formal expression for stochastic derivative. Now I leave for you the exercise to check that this is a really stochastic derivative of xt. What must be done? You can apply stochastic derivative to iterations and pass to the limit and get the same equation, and then say that the solution to this equation is the stochastic derivative of our initial Wiener function. As you see, we have a complicated Wiener functional solution to stochastic differential equation. Still, it has a nice representation for stochastic derivative. As I mentioned to you, the aim of application, one of the aims of application of stochastic calculus to the functional like this, like xt, is the derivation of condition when x will have a density with respect to the back measure. Let me recall you that from the general theory of diffusion processes, you know that the density of our solution xt, if it exists, is exactly fundamental solution to parabolic problem related to generator of the semi-group of x. And from this point of view, Hermander discovered his condition of hyperellipticity, which gives us sufficient condition for parabolic problem to have a smooth fundamental solution. And now we are going by other probabilistic way, which was discovered by Malal and Bismuth, and we will get the condition for existence of the density of our solution to stochastic differential equation in terms of stochastic derivative. But in order to do this, it occurs that we have not only study stochastic derivatives of our functionals, but also we have to study some good properties of extended or stochastic integral, exactly in this case when we consider Wiener functions. So let me recall what is the extended stochastic integral in our situation, and we will try to find some good properties of this stochastic integral. So let me recall you that together with the operator d, we have the operator which is just conjugated operator to d, and this e is acting from some domain in a space of square integrable regular functions now. To the space of random pairs. Yeah? And its action can be described as follows. If we have some random function xt, which belongs to this space, then xt for fixed t has an e to the next function. Yeah? So this is the sum from 0 to infinity. Here is the multiple integral n an. But now the kernel an depends on the additional variable t. So it will be looks like this: T, then T1, Tn, AT, and then DWT1, DWTN. So we have such a presentation, and let me recall that A is square integrated random kernel symmetric with respect to T1, T. Since xt is square integrated, then one can easily check. Please do this as an exercise. That an belongs to A2 0, 1, n plus 1. Just write expectation of the square here and do additional integration. But of course, in general case, there are no arguments that an is symmetric with respect to all this n plus 1. It is not true. But what we can do symmetrization. So one can do symmetrization. So let me denote by lambda n is a symmetrization of an with respect n plus 1 values. Then it can happen. It is not a common case, but it can happen that when we do such symmetrization and continue the following sum, and it will 0 to infinity. Here is n plus 1, 0, 1. Here is lambda an t1 tn plus 1 dwt1 dwtn plus 1. Then it can happen that this series converge, and if it is so, then we put the extended or square-root stochastic integral from the initial random function x to be equal to this sum. Our aim now is the following: to understand what is it, to find sufficient condition for x to be stochastically integrated, and then to find some relationship with stochastic derivative and so on, to study properties of this square-root stochastic integral. At this step, one, especially lazy students, can say, oh, why we have to study some additional stochastic integral? Because we already have good Ito integral, we have good theory of Ito integration, and so on. And there are a lot of people who successfully study ordinary stochastic differential equation without any knowledge about extended stochastic integral. Yes, it is true. But from other side, it will be very surprising for us that this is extension of the Ito integral. The first theorem which we will prove in the next lecture is the following. When x is adapted square integrated random function, this quantity exists and is equal to Ito integral. It is surprising. So we are doing something very abstract and something which is very far from Ito theory. And from this point of view, it looks like it has meaning in application to the Ito theory. Let me stop now for today. Maybe somebody have questions or comments, please. Okay, if no, then we will meet on the next lecture after a week. Thank you.